And then let's talk about the impact of atmosphere on sintering. Here, the chemistry part comes into play. It's quite often very, very complicated. Atmosphere leading to enhanced vapor transport inhibits, slows down, makes the sintering worse. Okay. Here we give you one example, which is iron oxide, Fe2O3, ferrous oxide, sintering in air versus sintering in argon, but this argon is contaminated by different concentration of hydrochloride. It's a argon, but with highly acidic vapor in them. Okay, not a very perfect example, I have to say, but this is what people observed. This is what people observed. Okay, in air, percentage density versus time reaching to the same temperature. So we are doing temperature, time, we are doing so-called isothermal sintering. Make sense? We reach this temperature and then hold for different time. If we are doing in air, you see, okay, start from this one 80 higher. Why? Because before reaching here, during the heating up stage, my sample already get partially sintered. Make sense? That's why it starts not from 50, but starts from 70, 80. Make sense? This is during the heating up stage, it's already been partially sintered. And then when you hold it, the density continues to increase to about 90, 95 if you do it in air. But then people find if they are doing this in argon, but with higher and higher and higher concentration of this acidic gas, right? HCl, the density goes not as high. How not as high? Depending on how much of the HCl in the atmosphere. If you have a lot of HCl, that essentially no densification at all. Okay, so this is the microstructure. If we are doing sintering in air, you see, okay, green, and then the green are reasonable sized, relatively dense. But when they do the sintering in the worst scenario, worst case scenario, 10 volume% of this highly acidic hydrogen chloride. You see the particles are individually, compared with the top, larger, but also rounder, right? And in between them, there seems to be a lot of gap, a lot of porosity. Make sense? So this is what we mentioned. Atmosphere leading to enhanced vapor inhibits sintering. And fundamentally, from chemistry point of view, sorry, the equation is not balanced. You see, catch my mistake? The equation is not balanced. But anyway, iron oxide plus hydrogen chloride forms iron chloride, but in a gas plus water. And all these gas vapor will make the gas transport faster and not really densify. And actually, we are etching. Do you see what I mean? In a way, we are, when you have HCl here, you are etching away iron oxide. Etching, removing iron oxide. Of course, you cannot expect it to be dense. Make sense? Addition of HCl enhance water transport, and to me, it's also etching and causing coarsening and reduced densification. Let's continue. Okay, here I do not have animation, but I will just continue. This one, another example of atmosphere on sintering. Very careful. We say here is PO2, the partial pressure of oxygen, also impact the oxidation state or valence, as well as the so-called volatility of your material. And as a result, impact your sintering or densification. Here, I'm showing magnesium chromium oxide. If you don't know how to call it, magnesium chromium oxide, MgCr2O4, spinel structure. And this plot is percentage of theoretical density, which is just the relative density, right? From 50 something, 50, 60, all the way to up to 100%. Make sense? You can be as high as fully dense. And then here where the horizontal axis would be partial pressure of oxygen, but with a negative sign, which means the left side is 0. It means it's kind of like a close to air. You see what I mean? The left side, PO2 log minus is 0, which means here you are roughly PO2 is 1, right? Close to 1, you are having 0. Make sense? On the other hand, this side means highly reducing, not oxidizing. Well, how oxidizing can you be, right? This is PO2 is negative 10 to the power of 12. Negative 10 to the power of 14. Make sense? This side is not 10 to the power of 12 of atmosphere of oxygen. No, it means you have very little oxygen. Negative 10 to, you don't forget they have a negative sign here, which means here I'm talking about a pretty inert or even reducing atmosphere. Very little oxygen. And then they are doing this so-called isothermal sintering at they are doing this sintering at different temperature, right? They are doing this at different temperature, and what do they find? If they are, for this material, if they are doing sintering close to air, they end up with a not as high density, not much higher than your green density. But on the other hand, when you start to using, let's say using hydrogen or carbon monoxide, something to reduce the oxygen content in your atmosphere, lower and lower, and combine that with higher and higher temperature, you can reach a density that is higher and higher. What does that mean? It means, okay, if I'm going to sinter this material, I have to be careful. I have to do it in an atmosphere that has very little oxygen. How do you do that? You can use hydrogen, one possibility. You can use carbon monoxide. Make sense? Or using some carbon in the system to scavenge, to suck the oxygen and in a sealed container so that I reach something like this. And at the same time, you reach high temperature. Of course, the temperature will still benefit you. But if you don't do this, if your atmosphere has a lot of, well, I wouldn't say a lot, but has enough oxygen, what you have is just low relative density. It doesn't really sinter. What people explained is evaporation of chromium oxygen species, volatile chromium oxygen species. Make sense? So that's a tricky point. Okay, which means to do this, you cannot just do this in our typical box furnace. You have to do that in a tube furnace that can sustain good vacuum, or you have to do that tube furnace with purged so-called hydrogen-argon mixture. Make sense? To remove your oxygen. Okay. Here is a related plot. We are plotting porosity on one side, relative density on the other side. Make sense? The higher the relative density, the lower the porosity. Here I have 10% porosity, I have 90% relative density. Make sense? The right side is relative density, the left side is porosity plotted in log scale. Okay, and then here we are looking at 3 different materials, but all these 3 contain not only oxide, but look at what I'm pointing. chromium, right? We are looking at 3 different materials, but all contain chromium. And which means the triangle for one material, the square for another material, the circle is for material. But you see, they pretty much follow the same trend, which means their densification is pretty much determined by the species that is chromium oxide. And what you learned? What you learned is, no matter what material is between these 3, you want to sinter in an atmosphere that has high PO2 or low PO2. Low PO2, 10 to the minus 12, something like that. But not in oxygen, or in air is roughly here. Make sense? Oxygen is 10 to, pure oxygen is here. Air is slightly lower than pure oxygen. But here you are we end up with density around 80, something like 80, 85. End up here, but not full density. It's only when you reduce the oxygen in the system that we can here. Of course, you still have to heat them up to an adequate temperature, right? You cannot expect full densification even if you are using reducing atmosphere. But if your temperature is only 1000, you still do not get to here. Make sense? You still have to heat up to 1700, roughly in that range. Make sense? But be careful with your atmosphere. And you achieve atmosphere with certain apparatus, like a tube furnace or a specially controlled, specially designed box furnace, but not with your typical open muffle or box furnace. Make sense? That gives you an idea, okay. And then I give some additional example, impacts of atmosphere on sintering. Some material, they would have so-called volatilization or even decomposition at high temperature. And here we give you some examples. One is beta aluminum, which is essentially aluminum oxide, but with a lot of sodium oxide in it. And you can imagine sodium oxide is a volatile species. So if I heat this whole thing up to too high temperature, what is going to happen? The sodium oxide would gradually evaporate. And if it evaporates, you don't have a high enough density. Make sense? The second example would be for piezoelectric ceramics, this so-called lead zirconate, lead zirconium oxide. And people find this, if you sinter this thing in open air, if the temperature is high and you find it doesn't sinter very well because over time the lead oxide continues to evaporate, continues to go away from your sample and into some other section of your furnace. The colder section of your furnace just leaves your sample. So for those can be problematic. Or when I was doing proton conducting oxide, this so-called barium, cerium, yttrium oxide, the loss of barium oxide. The barium goes everywhere when you heat up to high enough temperature. Or even silicon nitride for tooling. Silicon nitride, you heat up high enough, the silicon nitride, believe it or not, decomposes into silicon gas and the nitrogen gas. If you don't do it carefully, it's going to decompose. And all of these would inhibit densification. So some solution is so-called, read to yourself, protective sintering. You are immersing the material with a lot of other material that provides the material that is going to lose. Make sense? Here is we are having your sample and aluminum stopper and coarse pack powder. The same material, but you are packing it around it, loosely pack it, so that you provide the atmosphere, so that this part does not lose as much. You see what I mean? It still would lose, but not as much, because over here you already have a lot. And then on top, you put a so-called stopper. essentially you try to do some mechanism, engineering mechanism to restrict the loss of that volatile species. Make sense? Or some other related. We have lead zirconate. This is PLZT sample. This is the material that you are actually sintering. But then you look at it, beneath this PLZT, they put another setting plate, but with the same composition. They're using another material for sacrifice. And then they put aluminum crucible, and then in between them they put what? Lead zirconate, which essentially to provide you a lot of lead oxide so that the lead loss from the sample of your interest is reduced. Even doing that, you cannot avoid complete loss, but at least not 10% loss. I'm losing maybe 0.5%, 0.1%. Make sense? You're just doing, okay, something to try to make it lose less. That's so-called protective sintering. You don't have a good way to solve it, so you are just trying to sacrifice some other material to make it. Okay? And actually, we also did that for our own research. One of our students, the way he did this, he put this material, which contains barium, zirconium, cerium, yttrium, ytterbium, but whatever, and oxygen. The stuff that is going to leave would be the barium. Okay? What we observed is this material react with many other stuff. Like I'm using a crucible, but quite often my crucible is made out of aluminum oxide. But then what we find is this material, this so-called BZCYYB, react with aluminum oxide and form some other material, which means if I'm having just this palette, the barium would not only evaporate but also come down. So that's why when we do sintering, we put a lot of the same powder together and then put one palette on top, one palette below it. And then when we use it, we try to use the one in the middle. Kind of silly, but that's what we do as a so-called protected or sacrificial sintering. And then you see the difference. We are looking at the different sintering temperature for different 5-hour versus 10-hour. And then we are plotting the so-called weight loss for my sample or converted barium loss. And what we see is for the purple or for the red, purple or red, no matter what time we are talking about, we are having a lot of weight loss, which means barium loss. Weight loss is we put this much pellet in, we weigh it before sintering, and then after sintering we weigh it again. If no barium loss, I should have the same weight. My weight loss should be close to 0. But what we find, if we don't do this protection, 5-hour, 10-hour, we are having significant weight loss, meaning significant barium loss. And of course, naturally, the higher the temperature, the higher the loss. The longer the time, the more the loss. Makes sense, right? All this makes sense. And then when we do this so-called protected, at least covered, we kind of manage it to get the loss below roughly 2%. Not 0, but something that we can handle. Make sense? Not 0. Even after we do this, it's still not 0, but something we can handle, which we can tolerate. Okay? So you see the example. This is something, okay, you see, what are the knobs? I have temperature, I have time, and I have sometimes need to consider atmosphere. Not only atmosphere, sometimes I have to consider some protection. These are the different knobs when you start to deal with your practical material system, and it may be common. Okay, and here we are looking at the control atmosphere in sintering. What we plot here is a so-called big Allingham diagram. Allingham diagram. It's probably, if you forget, I would ask you to go back to your material engineering class, which essentially tells you different metal under what temperature, under what partial pressure of oxygen would start to oxidize. This plot, although it looks messy, it essentially tells you each line is for one. Each line is typically for one metal or one material. And vertical gives you horizontal. Vertical, you read the temperature. And then the horizontal scale gives you the partial pressure of oxygen, PO2. That's essentially what this plot is about. But it's based on this plot, we can predict a material under a given condition, temperature, atmosphere, whether the metal would oxidize or not. That's essentially what it is. Okay. And when we do sintering, quite often something like this, or thermodynamic database, nowadays people have that. It's very, very important when you consider. And for sintering, the process gas could be inert. Inert process gas could be argon, helium. If we're using nitrogen below a certain temperature, above certain temperature, nitrogen also is not exactly inert. And it's typical your commercial so-called UHP, ultra high purity grade, contains roughly 5 ppm, parts per million of oxygen or water. So just keep that in mind. Any cylinder, it says, okay, I have pure argon. Honestly, it's not pure argon. It's still argon, primarily argon, but with some concentration of water, concentration of oxygen. Okay, parts per million, which is parts per million. We're talking about 10 to the minus 6. 10 to the minus 6. Okay. Nitrogen gas, if we are using sintering nitride, quite often you have to use nitrogen gas. Oxidizing gas, air or oxygen. Reducing gas, quite often hydrogen, sometimes carbon monoxide, sometimes. Specialty gas mixture, people can mix different gas together to get certain atmosphere control. And PO2 control, if you want between 100% to roughly 0.01%, if you want your PO2 to be in this range, quite often you can just mix oxygen with certain inert gas. But if you want something that is on the ppm or ppb level, you have to use mixture, hydrogen water or carbon monoxide, carbon dioxide mixture. That will give you, this is what they mean, hydrogen water ratio, carbon monoxide, carbon dioxide ratio. That will give you the concentration that you want. Okay, I think let's stop here.